Let us revisit the function sine of x. We know that Taylor formula, Taylor series formula for sine x is sum as n goes from 0 to infinity of minus 1 to the power of n divided by 2n plus 1 factorial times x to the power of 2n plus 1. And we also know that its expansion is x minus x cubed by 3 factorial plus x to the power of 5 by 5 factorial minus x to the power of 7 by 7 factorial, and so on. When we plot this polynomial term by term, what happens? We have already seen this. So if the number of terms is 1, we get a straight line centered at x equal to 0. A little bit of construction. Let's take a point A on the function sine of x. I can move this around. So let's call it A. Let's draw a line through A parallel to the y-axis. And let's take the intersection between this parallel line to y-axis and the polynomial. And let's join these two and let's get rid of this line. And let's mark a point C on the x-axis, which is where it is being intersected by AB. Okay? So what do we have now? Remember, A is sine of C, where C is the point on the x-axis, which is being intersected by A and B. So A is sine of C and B is G of C, where G of X is the Taylor series up to one term. Now, as I move this, what happens? The magnitude of AB keeps changing. And when I take it to 0, what happens? Visually we may not be very accurate. So let's put in remainder, or what is also called as error. So here AB is equal to 0. And sine of x or sine of C, that is sine of 0, is also 0. So the Taylor expansion of one term is matching with the function. Now, if I take it a little bit this side or that side, you will notice that if I had rounded it off, it would have been 0. But there is an error. There is a gap between the function f of x and the graph of the Taylor's polynomial of one term. As I take it away from 0, the error seems to keep growing, this side or this side. Let's increase the number of terms to 2. When I take 2 terms, it doesn't change. Why? Because the second term is actually 0, which we have ignored here. If I take it to third term, this is what I get. Fourth term is also 0. Fifth. And you see what is happening to AB? Here, the error is this much, 5.91 something. And as I keep increasing the number of terms, the magnitude of AB keeps decreasing till it reaches 0. So that means what? Here, if I take this A nearer to 0, AB is 0. I'm not at x equal to 0. I'm a little bit away from the center. But after some time, an error starts creeping up. and the error keeps increasing as we go away from the center. Now let's say I have zero error. Let's make sure that it is zero. So at some point away from the center, it is still zero error. Now let me increase the center itself. Let's say x is not equal to zero. Rather, sine of x is not centered at x equal to 0, but it is centered at x equal to 1. See, the error has reduced. Again, if I center it at 2, error has increased. If I center it at 3, the error is much greater. As you must have figured out by now, there are two ways to reduce this remainder or error. One is increase the number of terms in the Taylor series used, and the other is to change the center nearer to the point of interest. How do you figure out this error? What is the formula for this remainder? That is what we are going to look at in the next session. So we are going to look at Taylor's theorem with the error term. That's it for now. Bye.